Okay, well, good morning, everyone. Welcome to the third day of this conference. So this morning, we've got a session on large-scale structure. We've got a really stellar lineup of speakers, so hopefully it'll be a really great session. And kicking off, we've got Uros Seljak. He's going to be telling us about weak lensing and galaxy clustering.
Thank you. So thank you, the organizers, for inviting me. So I thought I would say something about both weak lensing and galaxy clustering, since I'm probably the only plenary speaker talking about these things. And here's a quick overview. What are we talking about? I'll be talking basically mostly about the relationship between lensing and clustering and how we can exploit a lot of information from the combined probes, but also what we can learn just by weak lensing and just by galaxy clustering. So let me start with weak lensing, which we have heard already something about in the context of CMB. But the basic idea is that we have galaxies in the distant universe. As the light propagates through the universe, it's being deflected by the mass along the line of sight. And if you can imagine that if all the galaxies were circular in the beginning, then as the light propagates through the universe, it gets the circles become ellipses. They also get magnified or demagnified. So we may get a picture that looks like this in an ideal case. Spectacular cases of that are, for example, clusters of galaxies where we see these huge tangential arcs, tangential relative to the center of the mass. Okay, so the basic idea is of weak lensing is that this is sensitive to the total mass in the universe, both dark matter and baryonic. And so as such, therefore, it is probing mostly the dark matter, which is what we really want to know. And there are two methods that I'll be describing. One is where you look at the correlations between basically shapes of neighboring galaxies. For example, you look at correlations between these ellipticities. Let me show you the next slide, where basically what do we do here? We talk about convergence, where an image of galaxy is getting larger or smaller. And then we talk about the shearing, where we talk about either shear in this direction, or this and this. They're basically two independent shear components, which we call them gamma 1 and gamma 2. In Fourier space, the relationship between these things is very simple. And so we really say that we are just probing the convergence power spectrum, where convergence is some projected density along the line of sight. All right, so that's what we are. That's what weak lensing is sensitive to. And then, since this is just a projected density along the line of sight using some distant modulus, then the power spectrum of this thing is also just some projected power spectrum of the matter density. Note that it's projected matter density, not over density, and so this thing is proportional to omega matter times the amplitude of fluctuations, for example, sigma 8. All right, so people have done these predictions then for how sensitive this is to various cosmological parameters, and it turns out to be extremely sensitive, and that's why weak lensing nowadays is, one of the best probes of large-scale structure, and there are many different missions trying to go out and measure it. Let me show you the state of the art. Current state of the art in observations is CFHTLS. Which has already been mentioned yesterday, and this is a survey of about a few hundred square degrees, and basically they measure this shear correlations in two components, and the signal that has more components is this one, where they measure gamma 1, and the line is the best fitted theoretical model. The thing that I want to point out is this is still done on very small scales. We're talking about tens of arc minutes up to a degree. And because of that, it has some systematics, which have to do with the fact that on these scales, we also have to worry about what baryons are doing to the dark matter. I'll show this on the next slide. Another uncertainty that is always present in case of weak lensing surveys is that we have to know where those background galaxies are. What is their redshift distribution? And this may not actually be very well known. In this case, it's reasonably well known, but they cannot be completely certain because we do not have spectroscopic surveys to the same depth. All right, and finally, whenever you're talking about all the correlations of something, you always have to worry about additive systematics. For example, your instrument or your atmosphere or something like that can always add additional correlations, and that's hard sometimes hard to identify and sometimes hard to get rid of. And in this case, for example, they had to get rid of a lot of data due to the systematics like this. All right, so focusing on one theoretical uncertainty, I mentioned baryonic effects. What happens when galaxies are formed? The baryons have to cool first. They fall into the center of the dark matter halo. They drag perhaps a dark matter along with them. So that's one process which goes in the direction of enhancing the clustering. But there may be another opposite process where, for example, AGN feedback, where AGNs are throwing out massive amounts of gas, pushing them out of the galaxy perhaps, and again, perhaps dragging some of the dark matter along. And so these models are fairly uncertain. They're localized to to small scales in galaxies. But because we're looking, in the case of weak lensing, we're looking the whole projection along the line of sight, even if there's a galaxy nearby, where these effects are localized to small scales, they can still project to fairly large angular scales. And that's one of the problems in the case of weak lensing, which is that we can only observe it in angle. So here are some plots, and as a function of L, you can think of L as 1 over the angle, of how big these various effects are. You can see they can start to be important at the level of 3% already at L of perhaps a few hundred to 1,000. Right? Now, this is a relatively big problem for the CFHTLS survey that I showed you before. It's a smaller but not completely negligible problem also for CMB lensing. And the main reason for that it's a smaller problem is that CMB lensing actually is probing a much lower L values, much larger angular scales. And moreover, we are projecting, the sources are at highest possible redshift you can think of, right? The source for CMB lensing is at redshift 4,000. And so these are the largest possible distances. So we think that up to L of a few hundred, which is what Planck team, for example, has used, this is not a problem. All right. Let me now, so that's all I was going to say about just weak lensing in the sense of shear correlations. Let me now start talking about galaxies. And first of all, let's start with just an image. This is Sloan Digital Sky Survey. It's a fairly old image by now, but it makes the point that in Sloan Digital Sky Survey, we probe so-called main galaxies, which are like Milky Way type galaxies. And then we also probe luminous red galaxies, which are a lot brighter, and we can see them to a much larger redshift. You can already see by eye that these galaxies are clustered, so there's no shortage of signal in the case of galaxy clustering. So what you do is you go and you measure a correlation function or maybe a power spectrum of the clustering of these galaxies. These are very strong clustering signals, of order unity on scales of tens of megaparsecs. So signal is there, and it's much, much bigger than in the case of weak lensing. And moreover, since redshift surveys, when we measure the redshift of the galaxy, we measure three-dimensional position of the galaxy, we are getting three-dimensional information. So we have three-dimensional number of modes as opposed to 2 dimensions. And so that there's enormous amount of statistical power that one can get out of the galaxy redshift surveys. So that's the good news. The bad news is that when you look at what the galaxy power spectrum looks like, for those two data samples that I've shown you before, main sample and luminous red galaxies, they are not the same at all. They differ by a factor of 4, and moreover, even the shapes are not the same. All right. So clearly, we cannot just say we are measuring directly, dark matter power spectrum. So we have to do something else. We have to explain why this is different from dark matter, and how can we reconstruct dark matter out of this? Because otherwise, we're not learning anything from this. All right. So this is where the concept of galaxy bias comes in, and galaxy bias. Is the idea that basically galaxies are proportional to dark matter, but up to some, up to some function. And of course, if you don't know what that function is, then you haven't said anything about the relationship. All right. So on large scales, we think that this function is just a constant. Large scales being k less than, well, I'll show you a plot later, but k of order 10 to the minus 2 or so. The simplest explanation why there's a factor of 4 difference on large scales comes from the so-called peak background split picture, where we say, well, galaxies really have to form at the high density peaks of the dark matter, because that's the place where the dark matter will collapse and form halos. So we look at the high density peaks. For example, this is a one-dimensional slice of a dark matter, and we say, well, galaxy will only form at these peaks. And in fact, stuff has to go nonlinear. And so the overdensity has to be of order unity or more. So that's why I've drawn this line here, roughly at 2. And so when you put then a long wavelength fluctuation on top of this, then you see that you have pushed a lot of these points across the threshold of formation. But these points are now much more strongly clustered than the underlying long wavelength mode. All right, and so that's basic picture how we get this bias. How do we get the fact that galaxies are more strongly clustered than the underlying dark matter? The enhancement depends on basically how rare these peaks are. The rarer they are, the larger is the enhancement, and the larger this bias is. And so, for example, if you can show, for example, this first order bias, where you say galaxies are just proportional to the dark matter up to a number, you can show that this is just the derivative of the halo mass function with respect to the long wavelength over density. And because the halo mass function is dropping very steeply as we go to high masses, we find that this bias goes from roughly 1 at low mass halos, then can go up to 3, 5, 10, whatever. So this bias, therefore, the bigger the halo mass, the more biased the galaxies. And that explains the plot I've shown you before, which is that for low mass halos, like Milky Way, 10 to the 12, the biasing is of order unity. For large mass halos, like luminous red galaxies, which is a few times 10 to the 13, then the bias is more like 2. Okay, you can extend this picture further to second order biasing, still local. And you can do the same formalism, and you can show that basically this second order coefficient has to do something to do with second derivative of the halo mass function. All right, you can write the formula, and basically this is the prediction, theoretical prediction. The points here are from simulations. It roughly agrees with the simulations, let's say. There are other biases that I won't talk about here, but there's another effect that has to do with non-Gaussianity, probably non-Gaussianity, which I'll talk at the end. All right, but the bottom line here is if you add this second order bias, then of course this bias relationship between galaxies and the dark matter is no longer scale independent, becomes now scale dependent, and that can explain why the shapes are different. And I'm showing this on this plot. Now this is a plot from simulations where I've taken simulations and from different halo masses and shown relationship of that to the dark matter. And first of all, as I said, on large scales, this is constant, all right? And then on small scales, you see there are deviations, which are roughly predicted by the model I've shown you on a previous slide. All right? And then there are effects on small scales, which have to do with the fact that these are halos here I'm talking about, not galaxies, and so there's some exclusion effects that come in on small scales. All right, so this is, you can see there's a fairly strong scale-dependent biasing involved. And again, if you want to know about the shape of the dark matter power spectrum or correlation function, then you better know what this function looks like. Right? There is, however, another way to get to the dark matter power spectrum, which has to do that, well, this is what I'm showing here is the autocorrelation of halos or galaxies. Let's look at the same thing in terms of the cross correlation between halos or galaxies and dark matter. And it kind of looks very similar. All right, except on very small scales where we start to see the dark matter halo profiles, and these then become very, very, steep dark matter profiles. But if you look on few megaparsecs and larger, then this has very similar shape as the previous one, right? So again, it's constant, and then slightly rising maybe for these high halo masses, and then dropping off. So this suggests that if you combine then this cross correlation with the autocorrelation, maybe some of these scale-dependent biasing effects get rid of, and maybe even the large-scale bias can get rid of. For example, you can do the perturbation theory calculation that I won't go into it, but the quantity I want to investigate, actually, let me just skip this and show you the slide, the picture. If I define the cross-correlation coefficient in terms of the cross-correlation between halos and dark matter divided by the autocorrelations, square root of the autocorrelations, then it turns out that this thing is very close to 1, down to a few megaparsecs. You can see the deviation from 1 is only 1% even at 3 megaparsecs, very close to 1. And these are some of these theoretical predictions I've shown you on the previous slide, that suggest why this deviation is less than 1. But the bottom line here is really this is very, very close to 1%. So that suggests that if you can measure this and this, then and you know this, then you can reconstruct this. So how do we do this? we can, for example, measure this cross-correlation between halos and dark matter, again with weak lensing. But now it's weak lensing of a slightly different type, which has to do with weak lensing around objects, around galaxies. The basic idea is that around galaxies, if you map the shear field, you'll see that it looks something like this, tangential around it. And so you can do then you can average this shear from the background. Basically, you can average ellipticity from the background galaxies as a function of transient separation. And what you measure is the tangential shear, which you can express in terms of so-called differential surface mass density. It's basically mean surface mass density minus surface mass density at that radius. All right, so this is just some projected density, basically. All right, so you can rewrite this. If you average this over many, many galaxies, then basically these densities become correlation functions. In this case, for example, this surface mass density becomes just an integral over the correlation function. This is now correlation function between halos and dark matter. And this differential surface mass density, as I said, is again some complicated averaging of this projected correlation function. Now, I've shown you before that the correlation coefficient between halos and dark matter is 1, but only above a few megaparsecs. Below a few megaparsecs is actually very different from 1. You want to get rid of those small scales. But this surface mass density, differential surface mass density, actually has information from all scales, down to small scales. You want to get rid of this. There's a very simple way how to do this. You construct another statistic when you can show that this statistic then has all information from certain scale, which you have chosen, and above. So if you choose this scale to be few megaparsecs, then you have eliminated small scales. And this is shown here. This is this cross-correlation coefficient. Now, on the things that we can measure, this is what you get if you do it directly on this differential surface mass density. But if you do this trick that I just described, then this cross-correlation coefficient becomes very, very close to 1. And again, this is a theoretical prediction here from those theoretical models that even explain this deviation away from 1. All right, so as I said, if we know now this, we measure this and we measure this, we can reconstruct dark matter clustering using this technique. And this is shown here. This was done on simulations, realistic simulations of luminous red galaxies. And the gray line is the reconstruction that we get from the simulations. The blue line is theoretical prediction from nonlinear models, and red is linear models. This is just to say that we can reconstruct correctly, and that the effects are affected by nonlinear effects, because linear doesn't agree very well, but nonlinear does. Right? So we are probing, mildly a nonlinear regime in the case of the dark matter clustering. The first application of this was done last year on the DR7 SDSS data. Here I'm showing let me show you this one first. This is the projected autocorrelation function of the galaxies. These are main sample galaxies. And these are luminous red galaxies. Again, you see a factor of 3 difference here. Luminous red galaxies are much more strongly clustered. But the same offset you see also in this cross-correlation between galaxies and dark matter using this weak lensing. And so when you then reconstruct this, you find that this is basically proportional to bias squared. This is proportional to bias. You can combine these two, eliminate bias, and get a dark matter clustering. That's the basic idea. And the results we get, for example, the results for the bias are that these main sample galaxies have bias of around 1.3, and this nonlinear bias is essentially 0. But these luminous red galaxies have bias of 2.2, and they have very strong scale-dependent bias in the sense that this B2 parameter is very strongly away from 0. And then for cosmology, now once you have determined what bias is, then you know also what the dark matter clustering is. And these are the contours in terms of the sigma 8 and omega matter plane. And basically, you can combine them all into a single number, which is that this combination is given by roughly 0.8 plus or minus 0.05. I'll describe later. I'll show later how this compares to the other large-scale structure measurements, including Planck. But I just want to make the advertisement for upcoming results from the BOSS data. So this is SDSS third generation. So far, I'm just showing lensing signal here. So far, we have been using the green lines, the green points, and the red points. But now the new data that we have are the blue points. And you can see that the errors have shrunk by a factor of 2. So we expect that this method will, in the next iteration with the pulse data, will improve the results by another factor of 2, and then we'll probably get down to about 3% error on the amplitude sigma 8, which is quite competitive with the best weak lensing results. Okay, I just want to compare these two methods for weak lensing, right? One is shear, one is galaxy shear. The shear, as I said, is the one that is usually advocated as the method to do in weak lensing, but it does have several issues. For example, calibration bias. Well, calibration bias is an issue with both of them, but the intrinsic alignment, for example, is much more of an issue for shear than this method I described here. Baryonic effects are much more of an issue here than here. So there are a couple of reasons why maybe this method is competitive to the more standard shear method in the sense that it has fewer systematics. Okay, so that's all I wanted to say about this cross-correlation between galaxies and dark matter. Now let's talk about what about just galaxies alone? Can they provide information? In other words, can we just do large-scale structure survey of galaxies and just forget about weak lensing? Well, in principle, the answer is yes, but it's hard. So that's the bottom line that I will be talking about now. So how do we measure, for example, galaxy clustering, and how do we get the dark matter clustering out of the galaxy clustering without the weak lensing? The way to do this is to use redshift space distortions. Let me skip this. I'll talk about that later. But so redshift space distortions, the idea is that you have galaxies and you have other galaxies, and they are attracted towards this galaxy, and they're moving in this direction. And because in redshift space, because in redshift, what we measure is the position plus the velocity, peculiar velocity, then basically this galaxy in redshift is displaced from here to here, and from here to here, and you go from this kind of contours of constant density to these kind of contours. All right, so you get a squashing, and you can show that the squashing is, on large scales at least, is proportional to the logarithmic growth factor, because that's a relationship between velocity and density. And this logarithmic growth factor is something that is a simple function of omega. It's roughly omega to the 0.55 or so, this f. And so what we measure, therefore, we can measure essentially the amplitude of dark matter fluctuations times this f. We're measuring essentially velocity power spectrum on very large scales, and that has nothing to do with biasing, and therefore, in principle, this is a very powerful method to measure dark matter clustering without having to know what the bias is. So that's, in Fourier space, it's actually even easier to write this relationship between galaxies and dark matter. So there's a biasing term, and then there's an angular-dependent this velocity term, f mu square, where mu is the angle between the Fourier mode and the line of sight. All right, so along the line of sight, so for parallel modes, for modes parallel to the line of sight, there's a strong enhancement of clustering by factor of f. For the modes transitive to the line of sight, of course, then there is no peculiar velocity effect, and you're just probing the relationship between galaxies and dark matter in terms of biasing. All right, so if you probe this as a function of angle, therefore, you can learn about this f, and you can measure f times sigma 8. So that's on large scales. On small scales, unfortunately, you have other effects, nonlinear effects. The most known are the fingers of God, basically where you have inferior as objects. You have galaxies moving in random directions, but these velocities in various objects can be very large, and they can make these kind of fingers like this, which then can spoil statistics also on very large scales. So that's one of the reasons why this is very hard. In fact, let me show you in simulations these effects. I'm showing the monopole, just a straight power spectrum in redshift space relative to the linear theory. Let's focus redshift 0.5. These are the various halo power spectra. There's also one simulated galaxy power spectrum here, the blue line, and then there's dark matter. What you see is that, well, there are effects of order 5 to 10% already at k of 0.1, the deviations, and moreover, they're not the same for dark matter as they are for example, galaxies or halos. All right, so we need to, if we want to push this to small scales, then we need to understand these effects. It gets worse if we look at the quadrupole. Quadrupole is the leading order effect, which is sensitive to the velocity. All right, so that's shown here. And you see, again, very strong deviations away from linear theory. And this time already at k of 0.05, you already get 5 to 10% deviations. And again, they seem to be dependent on the halo mass. They seem to be dependent on whether it's dark matter versus halos and so on. All right, so very large nonlinear effects. So if you want to get amplitude fluctuations to few percent, clearly we need to understand these effects, because if we're just going to probe things at scales of k of 0.01, then we have very little statistical power. Usually when people tell you about predictions from Euclid or Daisy or whatever, they choose k of 0.1 or 0.2, right? So they go into the regime where these nonlinear effects are already very, very large. So several groups have been see how much can we model this, and I'm just showing you here an example from our group. We do manage to get a good model. For example, here I'm showing the monopole. These are different halo masses. You could just compare the black to black, these kind of lines. The models are good, but they come at a price of introducing several of these nonlinear biasing parameters. Right? In this case, we had to introduce 2. There are physical reasons why they should be there, at least 2, maybe more even. But you can see basically, you can get a good fit, but and you can explain why this is so, but it does come at a price of adding additional parameters. Similarly, for this quadrupole, again, if you look at this one here, you see, we do get a good fit against the simulations. And you can see basically, again, deviations relative to the linear theory, the dashed here is the linear theory, are already, as I said, 10% already at k of 0.05. But the models can actually explain why this is so. So there's some good news here that models can, in principle, get this information, but it is going to be very challenging, I think. Now, state of the art on the data side is BOSS. BOSS last year's data have measured this contour correlation functions. And if you zoom this one in, you get this. You get very similar pictures that I've shown you before. You see the fingers of God on small scales, and you see these squashed contours on larger scales. And if you take the best fitted value for f sigma 8, you can see it has an error of about 7% on the amplitude. So that's not quite competitive against of course, Planck lensing. But in the next iteration, this error should be reduced by another factor of 2. And then I think you will look much better. All right, so Sloan, BOSS survey, Sloan also measured the power spectrum, and I'm showing an example here. So if you want to just know the shape of the power spectrum, for example, to measure the neutrino mass, something like that, then that's also useful. Again, the current limits are still not yet competitive with other surveys, but it's getting there. Let me show a comparison here of Planck versus the rest of large-scale structure. This is the Planck point. As you all know, it has omega matter of about 0.31 and sigma 8 of about 0.81 or 2, plus or minus a few percent, so very small errors. And here I'm showing, just compressing these other data sets into, and I'm just showing 1 and 2 sigma contours of these various data sets. I'm not even showing you the central point, and I'm not showing this in 2 dimensions, just showing 1-dimensional, because most of these probes are just probing 1-dimensional combination of sigma 8 times omega matter to something like 0.5 or so. So here I'm showing these clusters from Planck. This has been already shown several times yesterday. It was shown more like this, right? A closed contour. I'm just showing 1-dimensional thing here. This is the CFHT-LS. This will be the central point. This will be 1 sigma, 2 sigma. This is this measurement that I mentioned from SDSS DR7 that we have done. It has very similar, actually, constraints to the CFHT-LS. And then the blue lines are these redshift space distortion results from Reed et al., again from BOSS, which, as I mentioned, they have larger errors. But one thing you will notice is that they are all to the left of Planck, right? So all of the large-scale structure surveys so far give you a slightly lower combination of omega matter and sigma 8 than Planck. All right. So each one on its own is not competitive, but if you combine them all together, then maybe one is starting to see some tension here. There is one exception. I really want to show this blast from the past. In 2005, we used to do Lyman alpha forest measurements. And in those days, we combined Lyman alpha forest measurements of the power spectrum amplitude at very small scales, 1 megaparsec, with WMAP, which at the time was here. And because the Lyman alpha forest was much larger amplitude than WMAP, there was actually some tension, like 2 sigma tension between them. We got very tight constraints on the sum of neutrino masses. Now, what happened since then is, well, the CMB data, Planck is now here. It's actually bang on Lyman alpha forest. So that's good news for us in the sense that, Lyman alpha forest wasn't that bad. But of course, the bad news is that now the neutrino mass limits, if we combined Lyman alpha forest with Planck, would have been weaker because this tension that was there before is no longer there. All right, so now I mentioned this because BOSS survey has a huge amount of Lyman alpha forest data. That's actually just been the first measurement of a one-dimensional power spectrum by a French group. And I think these Lyman alpha forest measurements of the power spectrum are in a bit of a revival now again, and you should expect to see a lot more new results, new analysis from this BOSS survey in the future. And then after that, even DAISY survey also has a plan to do Lyman alpha forest. Okay, in the remaining few minutes, let me just mention something about another thing that we can do with the galaxy surveys, which is to measure primordial non-Gaussianity. Primordial non-Gaussianity of local type is particularly nice because one can show that one can get a so-called scale-dependent bias on large scales due to this effect. In fact, the slide I've shown you before on the peak background split also has shown the derivation of this formula. You can just take a derivative of this with respect to the long wavelength mode fluctuation in the potential. And because you're probing potential as opposed to density, then you get an effect which shows up at large scales. So for example, here I'm showing a simulation without this effect, without this local FNL effect, and a simulation where this FNL is 100. You can see that there's a huge enhancement in clustering on large scales. But you can see basically also that because these are large scales, there are large fluctuations, large cosmic variance, sampling variance, and so on. So it's not that easy to actually get very small errors. So can one reduce the errors? And there are two ways. There are two main sources of errors in large-scale surveys. One is just the sampling variance, the fact that you have these fluctuating modes that you don't know what they are because they are drawn from a realization of a Gaussian random field. If you have two tracers, one that is biased and one that is not biased, I should mention, this effect here is proportional to b minus 1. So if your tracer is unbiased, then there is no effect. Okay? So now imagine you take two tracers, one that is biased, one that is not. In one case, there is an effect. In the other case, there is no effect. In both cases, the tracers are proportional to the underlying long wavelength fluctuation. That is, as I said, a Gaussian random variable. But if you take the ratio, this Gaussian random variable cancels, and what you're left is with the effect. All right? So you have basically eliminated sampling variance. So that's one idea how one can do things better. And the second idea is you can also reduce the other source of noise, which is the stochasticity noise. Basically, there's strong stochasticity between galaxies and dark matter. We usually call that shot noise. But you can actually reduce this shot noise by weighting galaxies by halo mass. If you do that, you're kind of making galaxies closer to the dark matter. And here I'm just showing basically the scatter plot between dark matter and halos. This is a standard scatter plot if you don't do this weighting, and this is what happens if you do this weighting. You can see how much the scatter has been reduced in this case. So if you combine these two things, then here is an example of how this ratio between biased and unbiased tracers looks like in a uniform weighting case. And from this example, for example, this is an example for something like a DAISY volume. You get errors of order 6%, 6 or 7. On the other hand, if you do this optimal weighting, then the errors shrink and you get errors of order 1 You can see basically how little scatter there is in this case if you do this weighting combined with this sampling variance cancellation. All right, so future surveys, could reach potentially FNL of order unity with these kind of techniques. That's from the power spectrum. But then there's also, of course, all of the analysis one can do in terms of the three-point function or the bispectrum. In the case of bispectrum, of course, you have a lot more triangles you can do and so on. And so there have been only a limited number of studies of this. But the bottom line of some of these studies that we have done seems to be that there's always more information in the bispectrum than in its power spectrum. And so, at least in the conventional analysis, without that sampling variance and shot noise cancellation techniques. And so there's hope that also from the bispectrum, one should be able to get competitive constraints against Planck. Right? And really, if we want to do this with large-scale structure, we really want to get down to FNL of order unity. If not, it's not all that interesting, right? But I think there is hope that we can get down to order unity. All right, so my conclusions are, so in the case of weak lensing, basically shear is very powerful. It's probing the dark total matter, but it's not that easy to actually get rid of some of the systematics and also some of the astrophysical effects like baryonic effects. I've tried to convince you that galaxy shear is a powerful alternative which gets rid of some of these systematics. And the current results, I would argue, are already some of the best on the market in the sense that in terms of statistical power, they're comparable to CFHTLS. And I've also shown you, the first results from the BOSS, which will reduce the errors by another factor of 2. So I think that probably will be the best weak lensing result on the market for a while. How long? Well, until the next generation of weak lensing surveys comes online, and they're already taking data. DS is already taking data. HST will take data soon, and KIDS is also already taking data. So there are several of these weak lensing surveys, next generation weak lensing surveys, which will really do a lot better on the weak lensing. In parallel, there are large-scale structure surveys from the galaxy surveys, and there also one can measure the amplitude of sigma 8 times f and things like that. Right now, it's not yet competitive, but I think next analysis of BOSS will already be competitive and will give errors of order 0.03. And then finally, when we have several of these, 0.03 error results, we can compare to Planck and see if that discrepancy that I mentioned will go away or will actually get strengthened. All right, so I'll stop there.
Okay, thanks very much, Uros. Do we have any questions?
So if I reverse your first point, if I say that, look, how much can we understand the baryonic feedback and baryonic effects from weak lensing, instead of asking that we don't know, but maybe, because lack of simulations and lack of many other things. So the question is how much we can learn about these baryonic effects in future.
Yeah, I guess I would argue that even in that case, it's better to go and look at individual objects and do this study using this cross-correlation between galaxies and dark matter, and then use that information to feed into this projected shear statistics rather than try to learn it from the shear statistic itself. Right? So in that sense, also this cross-correlation between galaxies and this galaxy shear lensing that I mentioned is a powerful way to exactly address that question of how much we are actually contaminated. Because there you can do it as a function of halo mass or galaxy luminosity. You can do it, you can patch together all the full range of galaxies and then, show how much effect it has on the shear statistics.
Uros, on this idea of weighting galaxies or halos by their mass to decrease the scatter, I'm wondering if you weight by the mass naively, you're weighting the rare objects more.
That's right. Yeah.
Which seems to go in the direction of making the short noise worse. So there must be some other effect that offset that. Could you explain what it is?
Yeah, so the simplest way to understand that thing is to think about dark matter in the halo picture, where all of the dark matter is inside the halos, right? And when you put all of that together, what you get dark matter. And dark matter has no shot noise, right? So that maybe helps you to understand how that magic gets away. It comes from the mass and momentum conservation, right? And basically for each big halo, there are smaller halos around and so on, so that when you weight the galaxy by that halo mass, you basically cancel out the shot noise, right?
Actually, I have a follow-up question. So that, even though I'm standing up here, which is, that's correct, but if you take real galaxy surveys, of course, what we see is the galaxies and not the halos. And so there's quite a large uncertainty on what the mass, halo mass that should be associated with each galaxy should be. And in addition, we only see the brighter galaxies, which typically means that the galaxies we see, their halos contain only 30 or 40% of the total mass. So given these two uncertainties, how much does this weaken the
Yes.
process you're talking about?
Right, so in fact, simulations we used were actually very poor mass resolution. We only resolved galaxies down to the 10 to the 13, so that would be kind of LRGs. So the second question that you addressed is, so we already get factors of several out of that. If we had used Millennium, then the results would have been amazing, right? Because then if you resolve down to the 10 to the 10, then you can reconstruct dark matter perfectly just with that sample. But even down to the 10 to the 13, you already get a factors of few. The first question was about, if there's scatter between the observable, such as luminosity of the galaxy, and the halo mass, how much does that spoil? And fortunately, the scatter, so we have addressed that. At 50% scatter, the errors get worse by a factor of 2 compared to, and then if the scatter is 20 or 30%, then there is no effect. Basically, it's just as good as any. The scatter is around 50% right now for clusters using optical information, but if you use other information, for example, like, I don't know, SZ information, something, then it could actually be lower. So, yeah, remains to be seen.
Okay, well, to keep on schedule, we should probably leave it there, but let's thank Uros again.